Hello everyone. Today we are starting with very important concept in computer architecture, something called as instruction set architecture or ISA. Why this is important? Because every piece of software you write, whether it's a small program in C or a large application, eventually both has to talk with the processor. But the processor only understands a very limited set of instructions. ISA defines exactly what those instructions are, how they look in memory, and how they behave. In other words, ISA is the common language between software and hardware. Without it, the these two simply cannot communicate. So let's go through our slides one by one and build a solid understanding. Instruction set architecture is the fundamental interface that defines how hardware runs software instructions. Think of it as a handshake between two parties, the programmer and the processor. Programmer uses instructions defined by ISA, and the processor guarantees it knows how to execute them. So whenever you write a program and compile it, the compiler converts it into machine instructions. And those instructions are understood because the processor implements that specific ISA or instruction architecture. The ISA can be seen from three different perspectives. First is hardware interface. This provides us a structured way for software to issue commands to the CPU and receive the results. Imagine it as a control panel of a machine. Software presses the right buttons and hardware responds. Second perspective is instruction format. This actually describes how instructions are represented in memory. The opcode, operands, or even addressing methods. Just like grammar defines how sentences are formed, instructions format define how instructions are laid out in binary. And third aspect is hardware software agreement. This is what ensures the portability. Once a program is compiled for an ISA, it can run on any processor that implements the ISA. That's why a program compiled for x86 runs on both Intel as well as AMD CPUs. Both follow the same ISA rule. In short, ISA is not about instructions. It is about compatibility, structure, and communication. Over the years, two main approaches have defined ISA design: CISC and RISC. Since 1970, the designers have asked, should instructions be complex, doing more work per instruction, or should they be simple, executing in fewer cycles? CISC and RISC are the two different approaches. CISC, that is complex instruction set computer, provides powerful complex instructions that may take several cycles. Whereas RISC, reduced instruction set computer, keeps instructions simple, usually fixed length, and ensures the fast execution. Both approaches have shaped computing, and even today, both coexist in different markets. The design of an ISA reflects the philosophy behind improving computing performance. CISC is focused on making instructions complex, so fewer lines of code were needed. RISC focused on making the instructions simple, so hardware could execute them very fast. And these two approaches are like two roads leading to the same destination, that is better performance, but they take different routes. So CISC programmer's convenience, and compact programs, whereas RISC prioritizes the hardware simplicity, speed, and efficiency. And this debate shaped how CPUs evolved over the last 50 years, and the results are still visible today. So let's talk about each one of them separately. So as we addressed, like these two approaches are the two roads. So let us address each of the road one by one. CISC architecture, complex instruction set computer. Let's talk about this in detail. It has three characteristics. Complex instructions. One instruction may do multiple things like fetching from memory, performing arithmetic, and writing back. Variable length. Instructions can be anywhere from 1 to 15 bytes. And this saves memory space but makes decoding very complex. And third characteristic is hardware intensive. The CPU uses microcode and extra decoding logic to execute these instructions. The idea here is let the hardware handle the complexity so the programmer or compiler doesn't have to write too many instructions. Now, when we do talk about these CISC instructions, they are like an all-in-one toolkit. They can perform multi-step processes in one instruction. They are variable in length, which makes code smaller, but decoding harder. And the reliance on hardware and microcode makes CPU more complex but powerful. The Swiss Army knife shown here is a single tool that contains many mini tools like knife, scissor, screwdriver, corkscrew, etc. It can do a lot, but because everything is packed inside, it is bulky, not very efficient for any one task, but harder to use quickly. The most successful CISC architecture is x86. It started with Intel's 8086 processor in 1978. Over the time, it evolved from 16-bit to 32-bit, that is IA32, then 64-bit, that is x86 64. New features were added, like for example SIMD, single instruction multiple data for parallel data operations, virtualizations for modular computing or modern computing. The greatest strength of x86 is the backward compatibility. Even today's Intel Core or AMD Ryzen processors can run software written decades ago. And that's why x86 remains dominant in desktops and servers because it combines strong performance with vast software ecosystem. The RISC architecture, reduced instruction set computer. RISC, on the other hand, simplifies everything. Single cycle execution, that most instructions complete in one clock cycle. Fixed length instructions, typically 32 bits, which simplifies this instruction decoding. And load store design. Only load and store instructions access memory. And that's why computation happens only in registers. And this makes hardware simpler and faster and also improves energy efficiency. And that's the reason why RISC became popular in mobile and embedded systems where efficiency is critical. So RISC architectures have their own set of advantages. Like instruction finish in one clock cycle, making performance predictable. Then all instructions are of the same length. And this simplifies the decoding and allows efficient processing or pipelining. The load store model means memory is the only accessed in specific instructions, keeping rest very fast. And energy efficiency is one of the biggest advantage, perfect for the portable devices. And the design philosophy made a RISC an ideal for the growth of mobile computing. ARM, the RISC driving the mobile era. The best known RISC implementation is ARM. ARM powers about 95% of smartphones worldwide. It dominates tablets and IoT markets with Apple's M1, M2, and now M3 chips. ARM is entering laptops and servers as well. ARM shows the power of RISC in real world applications, balancing the high performance with very low power consumption. So, if x86 represents the desktop era, ARM represents the mobile and IoT era. Imagine you want to cut vegetables in kitchen. You could use the tiny knife as we discussed earlier as an Swiss Army knife, but in it is very awkward. Instead, if you have a sharp kitchen knife, the job is faster and easier. And that's the difference between CISC and RISC. Now let us compare them side by side. Like CISC, variable length instruction, multi-cycle execution, complex hardware, compact programs. RISC with fixed length instructions, single cycle execution, simpler hardware, more instructions but faster throughput. So the key difference is CISC shifts complexity to hardware, whereas RISC, that is RISC, shifts complexity to the software. That is exactly the compilers. And each approach makes sense in different context. Finally, let's see what makes an ISA. Register set, which defines how many registers exist, their size, and their purposes. Data types, what formats are supported. That is, for example, integers, floating points, vectors, and so on. Addressing modes, different techniques for finding operands like immediate, direct, register, or even PC relative. And instruction classes, categories like arithmetic instructions, logical instructions, data movement instructions, control flow, system calls, or even domain specific instructions. And these are building blocks that define what a processor can do and how software must be written using this. So to wrap up, ISA is a hardware software contract, and there are two philosophies which dominate, that is CISC and RISC. x86 from CISC family still rules the desktop and servers, whereas ARM, that is RISC, dominates mobile and is moving into laptops and servers now. So the key components of ISA were registers, data type, addressing modes, and instruction classes. Define the processor's capabilities. And this is the foundation. In next session, we'll try to see how one can go deeper into the instruction formats and addressing modes to see how instructions are represented bit by bit. Thank you.